So this is our third episode, and today's speaker is Dr. Xian Shi, and he's right now a postdoc researcher in the Department of Mechanical Engineering at Stanford University, and he received his master and PhD degrees both in mechanical engineering at the University of California, Berkeley, and he also he obtained his bachelor degree from Tongji University in China, and his research interest includes reacting flows, materials, and their applications to energy and propulsion. And his current research related to detonation focuses on the understanding of the role of chemical kinetics in various detonation phenomena and developing suitable kinetic models for detonation numerical simulations. And today he's going to talk about his work to tackle this very interesting and very fundamental question: does the cellular structure of detonation determines its propagation limit? So I guess I will give the podium to Dr. Shi and let him to start his presentation. So please start when you are ready.
Awesome. Yeah, thanks, Chen. Let me share my screen. Okay, yeah, hi everyone. My name is Xian. Thanks for coming to my talk. First, I'd like to acknowledge the efforts that Xiao Cheng and his colleagues are making to put this talk series together and to keep us all connected. I personally look very much forward to more talks in the series, and also the discussion that we're going to have with fellow students and postdocs. So today I'm going to present some ongoing detonation research here at Stanford. The title of my talk is Does Cellular Structure of Detonation Determine its Propagation Limit? So first, I'd like to provide some basic context for people who may not be as familiar with this line of work. So first, I'd like to define the cellular structure and problem limits in the title. So speaking of cellular structures, I think for most of you guys, the first thing comes to your mind will be the classical soot volume measurement. And here is an example soot volume measurement we made here at Stanford for a stoichiometric hydrogen-oxygen mixture at 15 kilopascal initial pressure in a round tube. And you can see this fish scale or diamond shape-like structures, and you can actually measure the width of the cell size, denoted here by lambda, and also the length, denoted by L. So those length scales are extensively measured and documented for almost all the reactive mixture you can think of in the past few decades. And if you actually have a channel that have a high aspect ratio, rectangular cross-section, and you have a high quality imaging system, you can actually also see a similar features of the cellular structure through Cellular imaging. So here is a perfect example from researchers at University of Ottawa showing 4 snapshots of the methane oxygen cellular detonation propagation. So you can see those triple points are emerging together and creating a new ignition and going forward. And if you track the trajectory of those triple points, you can somehow recover this diamond shaped like structure is just similar to the soot volume. As far as the propagation limit is concerned, I think the most intuitive definition would be the inability to propagate, right? If you have a tube, you have a detonation in there. If you couldn't measure any pressure rise of the shock front, you're probably going to say the detonation fails in terms of propagation. So besides, you can also actually leveraging the soot foil technique to identify some of the limiting behaviors. So here is an example of the soot foil showing a spending detonation that measured by researchers across a few different institutions in Japan, that they measured a lean hydrogen-oxygen mixture at a limiting condition. So instead of having this fish scale-like cellular structures, you're gonna have the spiral-like structures. So this is somewhere in between a standard cellular structure to no structure, which marks the onset of the propagation limit. I think third, until recently, people in the community started looking at a concept called velocity deficit. Here is some results from a same Japanese group where they actually measure the actual detonation front propagation speed plotted with regard to the distance in the physical domain. Here is the distance from the ignition point. So if you look at the steady region in the back, you see that all the measurements, the propagation speeds, are well below this dCg value, which is the ideal Champern-Jouguet speed, right? And the difference between the actual propagation speed and the CJ speed is what we call velocity deficit. And this is a quantity that people are using to quantify the propagation limit, which is also going to be used in this talk as well. So in the past, I think people have spent a lot of effort studying the relationship between cellular structures and propagation limit, but mainly focusing on linking the cellular structure cell size to the size of the device. So for example, if you have a very long tube, in order for a detonation to propagate continuously in such a tube, you will need this critical diameter to be at least a third of the detonation cell width. Another example is if you have a detonation propagating in a tube and transition into unconfined space, and in order for that unconfined detonation to be initiated, you'll also need some minimum diameters. And here you can see for unstable detonation, you will need 13 times the detonation width, the cell width, and you will need 30 for a stable detonation. And for rotating detonation engine design, I think people also come with those empirical understanding. So on the left, I'm showing a numerical schematic of the RDE. And on the right, I'm showing the cross-sectional view of the annulus combustor. So you see that for the minimum diameter of the combustor, you will need 30 times the detonation cell width. And for the channel radical width, which just the channel width of the annulus, you will need 2.5 of the channel width, right? So those constants remain extremely valuable for practical applications, but they don't really tell us much about what's the physics behind the structure and the limits. Another issue that prevents us from understanding the relationship between cellular structure and propagation limits is also from the fact that until now, there has not been a way that people can study the cellular structure of detonation in a very clean manner. So here is what I mean. I'm showing again the soot-fall measurement for the stoichiometric mixture of hydrogen and oxygen at 15 kilopascals. At the same time, I'm showing the corresponding Z&D one-dimensional detonation simulation, where I plotted temperature and thermicity against the distance behind the shock. So as a classical one-dimensional detonation, you see the shock front over here, and you see the gradual temperature rise coincide with the heat release, right? So in a very common experimental setting, you would intuitively think that let's change the pressure and see what happens, right? So here is the result of the same mixture at 30 kilopascals. So from the soot-fall comparison, it's very straightforward. The soot-fall is reduced. The size or the width and the length of the cells are about the half of the base mixture. And now if you look at the Z&D profile, in comparison, a lot of things actually changed. If you look at this post-shock temperature, the 30 kilopascal case is slightly higher than the 15 kilopascal case. If you look at the heat release behavior, the 30 kilopascal case have a higher magnitude peak value and have an earlier heat release with regard to the distance from the shock front, right? So it's almost impossible to tell which of the changes actually leads to the change of the cellular structures. And you can actually see this similar phenomenon for a lot of experimental parametric studies. One more example here is equivalence ratio. So on the right, the soot-fall is a rich hydrogen-oxygen mixture at 15 kilopascals. So you see the cells are bigger than the base mixture and the Z&D profile. You see the heat release is a little later and also a little weaker. The fourth example is the argon dilution. So I'm always only changing one parameter at a time. So from the argon dilution, it's the same equivalence ratio, same pressure, but now you have 50% argon dilution. And now if you go back to the Z&D profile, they just look completely different. And it seems that by changing a normal experimental parameter, it's very hard to change one thing at a time and look at its impact at the cellular structure. So with this problem in mind, I'm going to divide my talk into 3 sections. So the first one, I'm going to talk about from kinetics to detonated cellular structures, where I'm going to tackle the problem I just described by doping ignition promoters, such as ozone, into the mixture. And hopefully we can examine the ignition kinetics and its impact on detonated cellular structures. And the second part, I will talk about the relationship between cellular structure and propagation limit, leveraging the tool of ozone doping. So the third part is an introduction to a new modeling approach that we pioneered here at Stanford, which was actually inspired through our attempt to understand why ozone is able to actually reduce the detonation cell size. So all the experimental data that will be presented in this talk are coming from this linear detonation facility here at Stanford. It's a classical driver plus test session setup, as you can see here. For the test session, we have 2 tube sizes. We have 2 round tubes. One is a larger one of a diameter of 32 millimeter, and a smaller one, 6 millimeter. And for the soot foil measurement, we insert a soot foil in the back of the test session and measure for a given condition. For the velocity deficit measurement, or just the propagation speed measurement, we have a variety of sensors, including pressure sensors in the driver section and optical sensor, as well as ion sensors in the test sections. I also want to acknowledge the main contributors to the work that I'm going to present here. Jackson Crane, who is a graduate student here in our lab, and Professor Hai Wang, the PI of the lab. And all the content from today's presentation is from these 3 publications. So feel free to find more details in those publications. Okay, now let's come back to the question that the problem that I described, that we cannot study cellular structure in a clean manner. So here I'm just showing again the cellular structure of the base mixture and the ZND profile. I can also define those 2 very frequently used terms, the induction length delta I and the exothermic length delta E, right? So the induction length describe the distance from the shock front to the peak Helios rate, and the exothermic length is basically the width of the heat release profile. So now, if we dope 3,000 ppm of ozone in the mixture, which is 0.3% of ozone in the mixtures, and here is what we got in the ZND profile. So for the ZND profile, you will see that nothing changed, but only the induction length, right? If you look at the post-shock temperature, they're the exact same between the ozone and non-ozone case. If you look at the shape of the heat release, they're the same between ozone and non-ozone. The only thing different is that the heat release is advanced, so the induction length is reduced. So the reason behind this is due to the ignition promoting nature of ozone, which readily decompose into molecular oxygen and oxygen radical, where oxygen radical is actually an important radical species for chain branching reactions, which will promote ignition, thus reduce the induction time, which translates into a reduced induction length. Okay. If you look at the experimental results, you see that the cell size is significantly reduced compared to the base case. It's about half of the cell size in the base mixtures. The degree of reduction actually pretty close to the degree of reduction of the induction length in the ZND profile. So we actually tested the ozone doping across a few different experimental parameter sweep. And here is just an example of the pressure sweep test, where I plot the cell width versus the initial pressure. So you see across all the pressure tested from 10 to 30 kilopascals, the cell reduction by ozone is always present. And moreover, you can actually fit the detonation cell size with a constant time, the induction length, which the constant value is actually already reported in the literature, and our results is in good agreement with all the literature value reported. So if you're curious why we pick 3,000 ppm ozone, here I'm also showing the cell reduction as a function of the ozone concentration. You see that immediately after ozone get into the mixture, you see a significant reduction in the cell width, and the reduction somehow plateaued around 3,000 to 4,000 ppm. So that 3,000 ppm is actually a concentration that is high enough that you can see a big difference in terms of cell reduction, but it's also low enough that is not able to change the thermodynamic property of the mixture. And that's the reason why in the ZND profile, the post-shock temperature stays the same, the heat release stays the same, because this trace amount of ozone is not able to change the thermodynamic behavior of the reactive mixture. So we also actually extend this measurement to limiting conditions. Here is an example of the same pressure sweep, but at a very low pressure. So you can see that the same trend was observed, where with decreasing pressure, the cell size increased dramatically. And for all the conditions tested, the reduction by ozone is still present. And also, if you compare the experimental results with the fitting, you see that initially there fits pretty well, and they start to diverge at lower pressures, which can be explained by a classical mode locking theory, where in a limiting condition, you would expect the cell to grow a little and become a little bigger than what is supposed to be measured in a non-limiting condition. So if you keep decreasing your pressure, you will get into the spinning detonation regime. We actually also measured the spinning energy in our lab, and showing here a representative soot foil. And if you keep decreasing your pressure, let's say in this case, it's below 2 kilopascals, we couldn't really measure anything that probably indicates a detonation failure, right? So the takeaway from this plot is that not only does ozone doping is able to reduce the cell size of a regular cellular structure, it also extends the onset of spinning detonation to a lower pressure. And that seems to indicate that ozone is able to extend the propagation limit. So let's verify that claim. So from previous slides, we confirmed that using ozone, you're able to tune the ignition kinetics of the mixture and tune the ignition kinetics only. And that leads to change in the structure. Does the change in structure actually going to lead to change in the limiting behavior? Let me bring back this experimental schematic to remind you what the velocity deficit is measured. So here we first measure the speed of the velocity in the driver session using those 3 pressure sensors. So here I'm plotting the normalized propagation velocity, which is the actual velocity d over the ideal CJ speed versus the physical distance of the device. So you see that in the driver, near the end of the driver, we have the velocity very close to 1, meaning that indeed a detonation is established in the driver. And then we use the optical fibers to measure the time arrival in the test sessions. And we take this steady region and we basically take the average value and measure the velocity deficit for the given condition. So here are some results. So first, this results is the velocity deficit measured in the 32 millimeter tube, where the normalized velocity is plotted against pressures. So the overall trend is quite clear, right? With decreasing pressure, you're approaching your detonation limits, so you're gonna have a lower and lower normalized velocity. If you run the same experiment with ozone, surprisingly, they're the same. They seem to contradict with what we found in previous slides, where there's a clear trend where ozone is reducing the detonation cell size, but when it comes to the velocity deficit, it seems that ozone does not have an effect at all, right? That's interesting. We also have a smaller tube, so let's look at the results in the smaller tube. On the right, I'm showing the same figure, but the results in the 6 millimeter tube. To notice that because it's a smaller geometry, you're expecting the detonation limits to happen at higher pressure. So the x-axis pressure range in the smaller tube is actually 10 to 15 kilopascal, while the larger tube is below 10 kilopascals. So for the 6 mm tube results, you can actually see initially, ozone and non-ozone cases are still very similar to each other. They're within their own measurement uncertainty. And at lower pressures, those two cases start to diverge. And in this area, you see that ozone is actually extending the limit by having a relatively higher d over dCj value compared to the non-ozone case, right? So with these two plots together, it seems to suggest that the velocity deficit will be a function of pressure, tube size, and ozone or non-ozone, and seem to be very complicated, right? So I think we will need a better analysis tool to understand what's going on here. In fact, in the literature, it has almost become a standard practice where the velocity deficit data are examined in this d over lambda domain. So instead of plotting the velocity deficit in the physical domain, here the plot showing d over dCj versus the tube diameter versus the detonation cell width, which is an attempt to see whether we can capture some of the effect from the tube size and also the cellular structure sizes. So let's look at our results in this type of normalization scheme. So first, I'm gonna show the non-ozone case from both tubes. It is encouraging that the two results from two different tubes are collapsing on one single curve. That means the d over lambda normalization is actually able to capture the tube size effect, which was also reported in the literature. Which is surprising is that now I'm showing the ozone case. While in the ozone case itself, the tube size effect is still captured, where those two results are on the same curve. But ozone and non-ozone case, they're actually separating, right? If you think about this normalization, d over lambda, the goal of using this d over lambda is actually to capture this normalized behavior of either the tube diameter and the detonation cell width. And for ozone, when it added to a mixture, it only changed the ignition kinetics without changing anything else and leads to a change in the cell width. So you would expect that such a normalization should be able to actually capture the ozone effect, but it didn't actually capture the effect. I think the first conclusion from this observation is that the deficit is not a single function of the cell width. Otherwise, the ozone effect should be captured by this d over lambda normalization, right? A second observation is, especially in the non-ozone case, you see with decreasing d over lambda value, the normalized velocity start to decreasing gradually, and when they arrive around 0.6, they start to drop rapidly, right? It seems to suggest there's two regimes on this detonation deficit curve. You can actually fit two curves to this two region that I talk about. And here are the formulation of the fittings. I'll come back to the formulation a little later. We did the same analysis actually for both methane oxygen mixture and methane oxygen ozone mixture as well. The trends are quite similar. So for both mixtures, the tube sizes are captured within its own mixture. The ozone and non-ozone are separated, just like oxygen, just like hydrogen oxygen case. You also have this sort of two-zone behavior where you have a gradual decreasing and a sharp drop. So here is what we hypothesize what happens. We think there are actually two regimes of detonation velocity deficit that are governed by two different physics. So here I'm actually dividing this velocity deficit data into two different zones, which are also actually represented by these two different fittings, the solid fittings and the dashed line fitting. And on the right, we call this region is loss carbon region, and on the left, we call the region is geometry limit region. So in the loss carbon region, we believe that the deficit is primarily determined by the losses to the tube wall, be it either heat or momentum or even mass divergence. So there is a few pieces of evidence why that's the case. So first, if you look at this fitting, it's 1 minus d over dCj is proportional to the inverse of d over lambda. If you take d to 0, you see actually the curve are going to go to minus infinity over here. So that actually is a reflection of the loss mechanism. Because if you think about, if you have extremely small diameter of tube, then you will have infinitely large surface volume ratio. And then you will have an infinitely large losses that will give you a very large velocity deficit. So the slope or the fitting of this curve is actually reflection of that type of physics. Second, in the paper, I didn't present it here, we actually tested a height and momentum loss model in a Z&D profile. And using such model, we were actually able to predict the deficit in the larger tube where we don't see the difference between the ozone and non-ozone. That's because the losses normally happens in the reaction zone where the ozone is only changing their induction zone. So in the loss region, Garvin regime, you would not expect ozone to make any difference because ozone is not modifying any of the thermodynamic property of the mixture, thus not affecting the loss behaviors. But if you now come to the geometry limit regime, where the asymptotic limits is becoming 1 over pi instead of 0, you will actually see that now the geometry start to matter. The d over lambda equal to 1 over pi actually represent one cell across the perimeter of the tube. So that passing this value, you're no longer able to establish any cell structure in the tube that will give you a limit condition, right? So that's why for all these 4 different mixtures, you will see the sharp drop near this 1 over pi value, which is representing the geometry accommodation limiting limits of the detonation. So now let's come back to the question we asked in the title. Does cellular structure determine its propagation limit? I guess the answer now is it depends, right? If your limit or your velocity deficit is in this loss Garvin region, you know that changing the cell structure not going to help you because it's not dictated by the cellular structures. But if your limits and your velocity deficit is in this geometry limit region, reducing the cell size will actually going to help you to extend the limits. So I'm going to give a brief summary before I move to the last part of the talk. So as I mentioned, first we confirmed from kinetics to structure through ozone doping. And we see that by adding a trace amount of ozone, we were able to significantly reduce the detonation cell width and extend the onset of the spinning detonation phenomena. And from structure to limit, in the physical domain, we see that in a 32 millimeter tube, there's literally very negligible ozone effect. But in the 6 millimeter tube, we see that ozone addition actually reduced the velocity deficit. And in this d over lambda domain, we identified these 2 different regimes. The first one is the loss Garvin, where the limit is insensitive to the detonation cellular dynamics. And in the second regime is the geometry limit regime, where it relies on the geometric accommodation of the cellular structure. So ozone will make an impact. So with that being said, if you dope ozone in the mixture, the ozone will be extending your detonation limit by moving the mixture away from its geometric detonation limit. So as a result, ozone is expected to promote detonation propagation in geometry limited detonation devices. Okay, so in a normal setting, I guess I will stop here and ask if you have any questions, but I guess I will just carry on. I think for many of you now, you may be asking this one question, which is, why does ozone addition reduce the detonation cell size in the first place, right? Although the V&D profiles seem to be telling, but it doesn't seem to explain any detailed processes in terms of cell formation. So I will start my last part by answering that question. First, I'd like to reveal some of the cell formation processes. Those are formation basics that may be very, some of you may be very familiar with this dynamics. So first, let me show a sequence of snapshots in a 2D simulation. So now we're looking at a basically a ignition at on the left side image, and this ignition will start to grow into a cylindrical blast, and until it was consumed by the two adjacent ignition and eventually get to the next blast. So essentially, this is a sequence of blasts. If you look at the detailed structures of the sequence blast, I also provide here a schematic which is similar to the second from the right image here, where you have a main front in the middle, and you have two Mach stem on the top and the bottom. So essentially what happens is that you will have a blast in the space, and because of a cylindrical blast, it will create a continuously decaying blast, where the pressure wave gonna gradually slows down, and the pressure and temperature front will gradually separate the wall. That basically creates this gray area here, which is the shocked but unreacted mixtures. And at the same time, you will have two adjacent simulations here on the top and the bottom, and their pressure waves are intersects with your incident detonation front to creating those two triple points, right? So the two triple points will eventually merge here to create a new ignition, and the trajectory of the triple points will create the cellular structure, essentially. So this dynamics is not only confirmed by simulation, is also observed in experiments. I'm bringing back this great Schlieren images where you can actually see some of the features in the Schlieren image recovered almost exactly compared to the simulation. So if you look at the first one, it's seem to be similar to the third from the right. And if you look at the second snapshot, actually this one is very similar to the second from the right for the simulation, also very similar to the schematic, where you see the decaying shock over here, and you see the two triple point over here and there. And I guess the third one is what you would have right after a new ignition, which is corresponding to this third one from the left. So as I mentioned, the triple point actually is what actually creates the detonation cell size. So you can actually mark what the detonation cell would look like on the simulation. Here is what is supposed to look like on the simulation. So if you want to know the cell length, you realize that the cell length is nothing but the distance between the first blast and the second blast, right? So now if you know the velocity profile of your shock and you integrate it over the entire cell lifetime, you will actually get the length of the cell. And as I mentioned, this blast is a cylindrical blast, so it undergoes from overdriven to underdriven with an average speed to be CJ speed, similar to what I showed here in the bottom. So that's how you can actually maintain a global propagation speed over as CJ speed. And if you integrate this velocity profile with regard to time, you will basically get the length of the cell, right? So it seems that understanding the dynamic of the velocity decaying function remains to be the key to understand the size of the cell. So the cylindrical blast can actually be quite readily modeled using even one-dimensional simulations. Here I'm basically showing an example of a one-dimensional blast that was done in a cylindrical domain. So you mimic this continuous decaying behavior of the blast. So on the top, I'm showing the temperature snapshots, and the bottom is the pressure snapshots with regard to the radius from the ignition. So you can actually see, especially in the temperature profile, the two fronts that I talk about. One is the pressure front in the front here, and also the maximum temperature gradient marking the temperature front. So you can track how they actually evolve with time. And here is basically how RP and RT evolve with time. So for any of the simulations, you will actually need a initial ignition kernel. So here I'm just taking a kernel of the size of R0, and I specify the thermodynamic states of the kernel to be equivalent to overdriven 1.6 value. What that means is that right after the ignition happens, the initial velocity of the pressure front will be 1.6 times the CG value, CG speed value, which is creating that overdriven initial speed. What I also drew here, the dashed line, is a constant CG speed velocity line. So the intersect between our P and the CG line is where the next ignition is supposed to happen, so that you can actually maintain a constant CG propagation speed globally. And the separation at that time between RP and RT is the unburned gas that where the new ignition gonna come from, right? So in experiments, it's basically this area that if essentially the two triple point are gonna compress this unburned gas to generating a new ignition. So here is where things get interesting. So what if I take the separation distance between pressure and temperature at this time and use that as a ignition kernel size for the next ignition? So now I have the R1 over here, and then I'm gonna creating a new blast and eventually get to a R2 value. So what I'm trying to mimic here is basically the sequence of blasts as I shown in the simulation, where you go from blast 1 to blast 2. So you can actually keep doing this exercise to get R3, R4, even Rn. And then the natural question is, do you think that is R value gonna eventually diverge or actually converge at a blend value? So let's confirm that. Again, this is only one simulation from one R0 value. In reality, we can actually run a few different simulations where we can use different R0 values. So here is just an example of 5 profiles from a very small R0 value to a larger R0 value. So after you have those array of simulation, you will get a few pairs of R0 and R1. So now we have all we need to play this game of blast sequence, right? So on the right, I'm plotting x-axis as R0, or here I said Ri, and the y-axis is Ri plus 1 minus Ri, which is also just R1 minus R0. Let's assume we have the R0 to be 1.2 here. So you check this curve, and then you look at the value of R1 minus R0, you got around 0.2. So now you know that your R1 gonna be 1.4. It's basically 1.2 plus 0.2, and you got over here. And then you look again and see that, oh, R2 minus R1 gonna be 0.1, you're gonna go to 1.5. And eventually you see that you will actually get a converged R0 value, which here shows is around 1.5, right? As I mentioned before, you can integrate the velocity profile of the decaying function to get the cell length, which is equivalent to here, the distance between RP and your initial kernel size. So this is your cell length. So for any given R0 value, you will actually have a corresponding cell length. So let's see. For the stabilized R0 value, you can actually calculate what the stabilized cell size is. Surprisingly, or actually not surprisingly, the predicted cell length is in a great agreement with experimental measurements. Because I think this blast dynamics actually capture most of the physics of how cells are formed. So now let's look at the ozone case, right? You can do the exact same analysis with a mixture that have ozone doping. And here is the results. Now everything seems to be quite clear. So first, if you look at this cell length versus R0, the ozone and non-ozone case are almost on top of each other. That's basically saying that for a given R0 value, you're gonna have almost identical RP dynamics, the pressure of the dynamic between the two mixtures. So that's expected because, again, ozone is not changing any of the thermodynamic property of the mixture, and the pressure decay is primarily determined by the gas dynamics of the mixture that ozone is not modifying. What ozone actually modifying is how fast the temperature front separates from this RP, right? Because the ignition promoting nature of ozone, it will slow down how fast the RP and RT separates. That basically makes the mixture stabilize at a smaller R0 value shown here. And you see that you're also going to see the same degree of reduction in the cell predictions that recover the experiments quite exactly. We also did the same test for a higher pressure case. So for both three cases, the predicted cell length value are actually in good match with experimental results. So we think this type of scheme of thinking about blast sequence provide us a new way to predict the detonation cell size for any given mixture. Furthermore, with this new understanding, we think now we can actually model detonation cellular propagation completely differently. So we call this new approach that we pioneered the geometric modeling of the detonation cellular propagation. We also call it DetoGem. It's a physics-based and a very low-cost modeling approach. So essentially, we're going to take all the 1D simulation of different kernel sizes as a library where we can learn all the dynamics about each and individual blast. So we will build this table that tabulates all this RT, RP value as a function of R0. And now we're going to create individual blasts in the space and figure out how they actually interact and creating the next blast. So here I'm actually showing three snapshots of this geometric modeling using those library from 1D simulation. You see there's 3 time snapshots, which is very similar to the Schlieren image that I showed before. If you look at over here, you see that the darker line represents the pressure front, the thin line represents the temperature front, the gray area is the unburned gas. So the geometric modeling actually recover most of the physics that we see in both direct numerical simulation and experiments. And with those 2 triple points colliding over here, you will have a new unburned gas pocket, and you will have the size of the pocket that you can go back to your library and creating a new ignition accordingly. So this approach actually is able to create those cellular structures quite readily. And here is actually an example of the cellular structure we generated from one of the text runs. So this model, as I mentioned, is relying on this 1D simulation tables. So in the space, it's actually analytical, and in the time, it's discretized. And the code is actually written in Python. The computational cost of such simulation is a few orders of magnitude lower than a direct numerical simulation, while it actually captures most of the cellular dynamic physics. So our hope is actually we're making the code more robust and tying up some of the loose end of the code. And we hope in the near future, we will publish the code on GitHub and share with everyone. I think our goal is to having this tool, at least a teaching tool that can get undergrad students very excited about detonation, or at best can be used as a tool to guide practical application design for rapid parametric studies. So with that, I'd like to end my talk with a few ideas for future work. First, in terms of the detonation propagation dynamics, I think nothing makes me personally more excited than having a practical detonation-based power device, be it either a rotating detonation engine or some other sort of power device concept. So studying the propagation in practical field and practical geometry is something I see a lot of potentials in. And in terms of the geometric modeling, I think we're only scratching the surface, as so far the mixtures we're looking at is either stable or weakly unstable. So all this sort of complex phenomenon that you will see in an unstable detonation mixture, including irregular cells, multi-level cells, also transverse wave interaction detonations, are actually not captured. So we hope in the next round of development, we'll be able to understand those physics and inject the physics into the geometric modeling. And the third, I'm going to just show it over here, is the 3-dimensional geometric modeling, which I think this is where it can really bring this new approach to the next level, right? While I think 3-dimensional direct numerical simulation is still remain to be the holy grail, I hope that we can learn some of the physics from both experiments and numerical simulations so that we can actually have a good understanding of the three-dimensional dynamics. And last but not least, let me acknowledge the funding support for all the work that I presented here by Air Force Office of Scientific Research, as well as the Graduate Student Fellowship from National Science Foundation and Stanford University. So with that, I'd like to conclude my talk, and I'm happy to discuss any questions or comments that you may have. Thank you.
Yeah, thank you, Dr. Shi. I think this is very interesting and very inspirational talk, and a lot of this new ideas of having this low physics or reduced order modeling. I think it's quite novel to me, and yeah, I think like there's definitely a lot of directions that you and the whole community can explore using this model.
Dr. Shi.
Hello, yeah.
Yeah, I'm Cesar from Spain. Nice presentation, by the way. Yeah, I like it very much. And I have a question about the model you showed. I mean, the last thing about the blast wave model.
Okay.
What is the initial setup? I mean, because blast wave by themselves, they lack of scales. So you must at first guess at first configuration in the transverse direction of these initial blast waves, and this is something that has it might be something related with the induction length, right? I mean, at least at the very beginning.
Okay, so let me make sure that I understand your question. So are you talking about how we initialized this geometry modeling?
Yeah.
So you're asking that?
Yes.
Okay. So actually, I should have a plot to show. Let me see. I can find it. All right, give me a second. Okay, here. Share my screen again. So here is an example of what would look like in the simulation, where we will have to actually have a dense network of the initial blasts, and those initial blasts will eventually grow into this sort of mold-locked cell structures. I think you can see it as a reflection of probably some of the DDT, how DDT would happen, where you're going to have the turbulent flame interactions of creating all the sort of small blasts and eventually grow into a detonation. But I think, yeah, that's how we actually initialized the geometric modeling.
And they all, I mean, independently of the initial conditions, they all end up with the same pattern.
As you can see here, at least for this particular settings, we're testing two different channel widths, right? So you see that for different channel widths, you will end up having a different cell sizes. So the boundary condition, as well as, well, I guess in this case, the boundary condition will creating a different pattern. And it should not be, at least for our initial explorations, dependent on the initial conditions. So it should always sort of converge into this mode locking behavior based on your boundary conditions and the size of the channel.
Yeah. I mean, yeah, I see. Mm-hmm. I think it's clear for me now. Thank you.
Yeah,
and congratulations again.
Thank you for the question. Let me ask one question. Also about this dead jam model. You talk about this. You obtain this 1D library for blast decaying. So this blast decaying, you actually you somehow like you have this initial energy source by recording the length separation between this temperature and the pressure front. And this whole 1D blast decaying is just like a inert medium, is it? Or it is
back to let me go back to the profile.
Right.
I guess, I think, sorry. So this one should be.
Yeah.
Having.
Yeah, I'm asking like these two figures on the left, are this 1D simulation in inert medium or is also in a reactive medium?
So it's completely reactive media. So the composition of the mixture is homogeneous. And in this case, it will just be stoichiometric hydrogen and oxygen mixtures. So that actually the pressure front is actually a reactive front. So you will actually see the separation. Otherwise, I think you wouldn't really see such sort of close-up reaction front from the pressure front, right?
Oh, I see. I see.
Yeah.
So, like, eventually, have you compared the CJ velocity of your reduced order model to what you can get just from the CJ formula?
Right.
I just wonder in this case, how can you make sure like the energy conservation is satisfied? Right.
So I think in the 1D analysis that we did here, as you can see that we always sort of taking the intersect from the RP with these constant CJ speed line. So that kind of indicating we're trying to conserve the CJ speed globally by doing that, right? Mm-hmm. So actually in the simulation, let me see again, should be able to get there. We actually also measured it. So I think in this plot, you can actually see the front, the upper plot, we're actually tracking the front of how it propagates. So it's approximately around 1 in terms of the normalized velocity. So we're preserved the speed. But as you can see that there's still oscillation in there and there's something we're still looking into. Yeah.
Okay, I understand. Okay, thank you. Thank you for the answer. Yeah, I think there is a question from Professor Higgins. Could you just unmute yourself and ask?
Okay. Yes, thank you, Dr. Shi. That was a very interesting talk, and I think the geometric approach to modeling the detonation dynamics looks very, very promising. So I would certainly encourage you to keep going down that path as far as you can.
Thanks.
I'm thinking about how to extend that model to problems that are of a lot of interest right now, like the problem that was the first part of your talk, where you have a detonation deficit in a tube, presumably due to mass and momentum and heat transfer losses to the wall of the tube, to the boundary layer, or the so-called negative boundary layer that builds up on the wall. Mm. Or you mentioned there's a lot of interest now in rotating detonation engine, where you have a reactive layer that's essentially on one side confined by the combustion products from the previous cycle of the rotating detonation engine. Right. So in those cases, the fact that you see a velocity deficit is due to a couple of factors. One is there's mass and momentum loss to the boundary, and I guess that could be easily modeled by just allowing the blast wave to propagate out and not come back, or attenuating it in some way. But there's also likely an effect due to the fact that these kernels, these little detonation source kernels, experience some expansion due to the release of confinement.
So yeah, I have some thoughts. I think maybe Jackson also have something to say about this geometric modeling. But in my mind, yes, I think those are critical physics that we're target to include in the model. I think in particular, let's say for the heat momentum loss, I think we can either sort of tackle it at the boundaries, where we can actually have those sort of loss terms built in how we treated the boundaries. I think also we can actually, let's see, establish a new library of the 1D simulation where we can have the loss terms directly embedded in the 1D simulations to sort of capture that phenomenon, right? And I think for the confinement you were talking about, we actually also thought about it where, what if you actually have a boundary where it's transmissive, but is inert gas on the other side, right? So we actually explore about having one boundary as a reflective boundary and another boundary as transmissive with inert gases on the top, and see how the detonation could stabilize or not. So I think now we're actually exploring all these directions, but I think we're still kind of trying to make sure the code for all the canonical domains that can work perfectly, and we will have more confidence in those special cases and hoping that will give us the right physics. But yeah, that's a great comment. I think we have been working towards that direction quite evidently. And hopefully we can get something from those special cases.
Yeah, I think that's a great answer.
Thank you.
This is Jackson Kratom, Stanford here as well. Just to add on a little bit, you know, one of the great utilities of the geometric model, or DetGem as we call it, is that it's really easy to model any type of geometry or any type of boundary condition you want. And so I think at the very end of Xian's talk, he showed just a little teaser of the model operating in a kind of a U-bend type geometry, or something that's representative of an RDE sort of. And actually we see basically very perfect shock focusing effects in the basically converging wall, just like we would expect from experiments. So it's very encouraging. We've also done simulations with, like Xian mentioned, basically one perfectly transmissive wall and one reflecting wall. And again, we see the dynamics we'd expect. And all that being said, you know, the physics that's embedded in the model is very simple. It's only what you've seen here. It's basically this kernel stabilization effect that we showed physically, and nothing else. And so there is still a lot of physics that are missing. And I think to us, it's almost surprising at how well it works, given the simple physics that are in there. And it's certainly going to be something of ongoing work to determine some of the I guess, higher order physics that exist, certainly in more complex detonations like unstable detonations, but even exist in some of the more straightforward cases. So that's something that we'll work on into the future.
Great, thank you for your answer. Yeah.
Yeah, thank you for the answer. Is there any other questions or comments from the audience? You can either raise your hand or just directly unmute yourself and ask.
Yeah, let me put back on the last slides so that people can email us. If they have any questions, they can email us as well.
Right.
Yeah.
Yeah, actually, I have a further question, or just about like what is like how hard is this thing going to be to extend to 3D? I think most of the cellular, like you can see, like in the literatures, there are a lot of comparison between numerically obtained cell size to experimental values. Right. But I don't think those are very, you know, like, because if you are comparing only 2D simulation with this realistic cell size obtained from 3D structure, I just don't know how valid this is. I think it's perhaps only if we can extend the simulation, either higher order or reduced order simulation to 3D, then this comparison between numerical result and the experimental measurement of cell size become valid, right? What would
I think to answer your question, maybe I think that's something you could teach me about how three-dimensional simulation actually works. I guess it's very clear, at least in the 2D domain, you have this diamond shape dictated stabilization mechanism where you can perfectly take advantage of that doing the geometric modeling, right? So in 3D, in my mind, is that we cannot even first find a unit cell like the diamond in the 2D to even talk about stabilization, right? As far as I can tell when I look into literature about all the three-dimensional simulations, I think most of them are actually a sort of mode lock quasi-2D simulation where the waves are all stretched. They're not actually a spherical blast. They were rather some like planar waves bouncing like around walls, right? So in that sense, that actually recovered 2D sense. But if you think about now, if we have a very large tube, I would expect all the blasts in the third-dimensional space to be spherical blasts. If they are spherical blasts, then what is this new ignition mechanism, and what is the stability that actually keep the detonation from going forward. I think that's part of physics, at least for me, is still very unclear. So I think the availability of geometric modeling will largely depends on that part of physical understanding. And then we can start to sort of establish how we can formulate the whole thing, right? So that's something that I'm look very much forward to learn in the future from like the numerical simulation experts about. Eventually, I hope we will arrive at a stage where we can afford those very large three-dimensional simulation where we can look at the results and see whether is there a three-dimensional stability mechanism or it's always about the wall regulating it, right? Okay. So that's kind of what I'm thinking right now. Yeah.
Okay. Yeah. Thank you. Thank you. Actually, just further from that comment, I think like for most of the three-dimensional simulations right now, I see in the literature, and I guess one of our speaker, Saeed Taleb, he would probably present some of his results on 3D simulations. I think, as you said, like because of the limiting computational resources or this high cost associated with 3D simulations, the domain size is actually small. It's kind of like only about like one characteristic cell size. So the whole dynamics is perhaps not the intrinsic dynamics associated with the mixture, but it's a result of your geometrically locked domain. So I just think like right now, as far as I can see, I don't think like all this the the 3D simulations can provide us 100% valid result for us to infer some physics to build into this this reduced order or geometric based model. But I think is perhaps like from the experiments or from some experimental observations or this macroscopic measurement from experiments is perhaps a better source to provide some insight into this 3D structure. Just my feeling. Yeah.
I think just to add on that, I think this, as I showed here, this head-on soot foil on the right, it's actually something that can be very telling, right? I think for most of the simulation, 3D simulation, if you try to derive this head-on soot foils, because of the limiting geometries, you normally get square cells because all the waves are planar wave cutting into each other instead of spherical. But in experiments, for this tube, at least, you see there's very chaotic behavior where I think those are all sort of spherical blast that doesn't creating a perfect structure. So I think that is where the new physics should come from.
Okay. Okay. Yeah. Interesting. Thank you. Thank you for your answer. Yeah. Is there any other questions or comments? If not, if you have further questions or you want to know more details of Dr. Shi and his colleagues' work, please note down his email and you can email them your questions and comments. And also maybe Dr. Shi, you can go back to the page where you show the recent publications, and
sure.
Yeah, people can have a note of this.
Oops. All right, here we go. Okay.
Yeah, I guess all of these are already available online, right?
Yep.
Okay, great. Yeah, you can take note of these publications, and we will be editing the videos, and eventually we'll post the videos to YouTube after Dr. Shi and his colleagues check, and once we get their permission, and we will upload the videos, and you can have further discussion on the chat or the comments for the videos there as well. And yeah, I hope that all of you can keep participating in this forum, and we can have a further discussions, and then we have more talks to come in this fall. And today, yeah, I would like to thank Dr. Xian Shi again. And this is very interesting talk, very inspirational work, and also Mr. Jackson Crane. I guess like they will, continue exploring this direction, and we like to see more work from them. And also, hopefully, we can have some collaboration opportunities in the future. Right? Yeah, thank you very much, and
thanks for organizing.
Yeah, thank you, and thank you all very much. Thank you all for attending. I will end the meeting here, and see you next time. Have a great day. Bye bye.
Thanks, everyone.
Thank you. Bye bye.
Bye.